Here we go. There we go. So your job is to make sure this, if this says something, that means it's not recording. So, but don't stare at it, right? So, just help me out. If something weird happens, or it shuts on, like it's black, dark, right? Then something's wrong.
I feel like you should have it like up there.
Yeah, I should. But Mr. McConnelly and Mr. Baker built that contraption, and that's what fits the iPad. I don't have anything to suspend it. I would, if that thing could hang from there, it'd be perfect. But that's fine.
It falls down and smash it.
All right, now.
Hold it and then like hook a bungee cord up and then like take the bungee cord out.
Yeah, probably. I mean, believe it or not, I have like a ton of stuff to do as a teacher, so that's not really.
Why do you have it pointing that way though? Like you could have it like there.
Because then it's blocking your face.
And also it has an angle of like the whole board.
Yeah, I've been doing this for a long time. This
He's a
works perfect.
professional.
All right.
Yeah, but he never.
So,
He's
now.
a YouTuber.
Now all this is being recorded, so stop it. All right. What did we write down in our notes last, though? We did the demonstration, but the balance stuff?
Yeah.
All right, good. So before I actually give you notes on properties, because that's what that demo was about, and we'll review that, we need to write this down. This is really important. Elements. So this is continuing the notes on valence electrons, even though I kind of switched gears. Elements in the same group have the same number of valence electrons. Same number of valence electrons. And when I do E minus, that means electrons, because electrons are negative, and that's the symbol for it. Same number of valence electrons. And what does that mean? That means elements in a group have similar properties. So, not only being able to tell me how many protons and electrons and neutrons these atoms have, and tell me what the electron configuration is, and tell me how many valence electrons. So you've already learned a lot, actually. So being able to tell me all of that, this is like the final part. If something has 2 valence electrons, it's going to react very similar to something else that has 2 valence electrons. So magnesium and calcium, for example, are in the same group. They react very similarly. Sodium and potassium, I have both of those. We're going to put them in water, and you'll see what happens. They should react similarly. They do. All right? Try and give you another example. Silver and gold, they're in the same group, Ag and Au. They're kind of similar. Yeah, they look different. They're both used for jewelry, pretty rare. Precious metals, right? So I'm just trying to give you examples there. Okay, so that was it for that. I just want to make sure I'm not forgetting something here. Well, I guess, you know what, we can do this first before we do the properties. Okay, as far as reactivity is concerned, so let's do this here. Let's get down, let's do this one. Let's do, and then we're going to write period 3 in our notes from left to right. Na, Mg, Al, Si, P, S, Cl, Ar. The spacing between is like irrelevant. Don't worry about that. Alright. So we're going to get that in our notes, and we're going to talk about as we move from Na toward Ar. So as we go this direction, a bunch of things happen. So as you move left to right on the periodic table, doesn't matter which period you pick, 1, 2, 3, 4, 5, 6, 7, whatever. Pick a period. As you go left to right, something happens. Now I'm going to kind of lead you and see if you guys can come up with it. I'm going to talk about reactivity. That one I'll probably have to just give you, but the other one you might be able to get. So let's say you're standing on this line here. If you walk towards Na, or you walk towards Ar, which direction, raise your hands, which direction would you become more metallic? So if you're standing in the middle, and you can go this way, or you can go that way, which direction will you become more metallic? And again, I treat it as if it's like you're turning into these things, just to help us kind of visualize that. Left. Right. So, correct. So if we're standing here, and we go over here, we are going to become more like a metal. Why?
Because it's on the left.
Right. Correct. Forever. So yeah, all the metals are on the left side here, and all what's over here?
Non-metal.
Non-metals. Good. So, if I was to ask you guys, as I move left to right, so now we're starting here. We move left to right. What happens to the metallic character of these elements? Just think for a second. You may not know what the phrase means, but just think about what we just said. As we move left to right, so we're going from here to here to here to here to here, what happens to the metallic character? And this goes for the entire chart. So you start on the left and you're walking to the right. What happens to the metallic character of these elements?
It becomes weaker
Good, or decreases. Yes, why?
because you're getting closer to the non-metals.
Right. So, metallic character, what do you guys think that means? Lex, what do you think that means? Metallic character.
That there's like metals as metals.
They're metals, they behave like metals maybe?
Yeah.
Good. Act like metals, right? Like your character is kind of like how you act. So metals act a certain way, non-metals act a certain way, react. So yes, as we move from here to AR, the metallic character will decrease. Let's write that down. Metallic, so underneath this arrow, so we're going left to right, metallic character decreases. That should make perfect sense. If you're standing on the left with all the metals, that's where all the metals are, so that's how they're going to act. They're going to act like metals. But as you progress and you get to the right side of this chart, there's no more metals. Right here is the metalloid. This one kind of has both properties, but once you cross that, now these don't really have any metallic character at all. They have what's called non-metallic character. I'm not going to write that. But as metallic character decreases, we are moving left to right. What if we went right to left? It would be the opposite, right? The metallic character would increase. I'm not going to write that either. All I'm getting you to understand is if you're over on this side of the chart, that's where metals really act like metals. And as you progress to the right, you don't really have metals, you have non-metals, so they act like non-metals. That's what this phrase means. I used to spend a lot of time defining it and writing notes. I think it's better to just visualize it, see the elements, and just understand if you're hanging out with metals, you're going to act like metals. If you're hanging out with non-metals, you're not going to act like metals. So the metallic character decrease. Yeah.
So the further you go to the left, the less of a metal something becomes. So like ruthenium 44 is less of a metal than ruthenium.
You mean further to the right. Yeah, as you move right, you become less metallic. Correct. Here's the crazy part. What do we use to build everything out of, basically? Steel. Steel has iron in it. Here's iron. Potassium is a way better metal than steel, than iron. So what class are we sitting in? Chemistry. So in chemistry labs, chemical reactions, how things react. Group 1, sodium, potassium, these guys are the best. There's no metals that are more reactive than them. As we move this way, metals are very strong. Iron is strong, copper, zinc. They have very different properties than these, but in chemical terms, they're not as good of a metal. They're less metallic in chemical terms. In real life, it's different. Like building materials, screws, nails, hammers, building materials, we want these metals in the middle. They're hard. All right, they're very hard. These metals are actually very soft. I'm going to show you, if not today, tomorrow. I can cut these with a knife, like a butter knife. I can actually probably squish it with my hand, but it'll burn my hand, so I don't do it. So these are very, very squishy, malleable. Okay, these not so much. So this is true in chemistry as far as chemical reactions, but in real life with physical uses, the metals further away, like these in the middle here, are better. That's a good question, Paul, and that's something I was going to bring up. So, metallic character basically means how well does it react like a metal, or how well does it react like a non-metal. So, next thing we're going to write here. Group 1, most reactive metals. Most reactive metals. And that's what I mean by metallic character. So in this class, that's what we mean when we say a good metal. We mean how well does it react. So group 1 is the most reactive metals. So now, let's think back to what we've learned. Why do elements react? Raise your hands. What are you doing?
The heights.
Oh, yeah, that's funny. The sensor's in the back of the room. Yeah, you can go ahead, take a walk.
Get out.
Walk right to the goggle cabinet, then take a left. Now walk straight. Keep going. Trust me, I got you. Keep going. There you go. Okay. All right. Question, comment, answer. What did I ask? Did I just ask a question?
Why do elements react?
Why do elements react, Paul?
To become noble.
Right. They want a full valence shell. How many valence electrons does group 1 have? 1. What if it loses that one? Look at group 1. How many does it have? 8. So that's why it's the most reactive, because all it's got to do is lose 1. Group 2 has to lose 2. It's a little harder.
Well, then shouldn't like group 17 be the same?
You're ruining my fun,
What do you
Cyrus.
mean ruining your fun?
That was where I'm heading.
Oh.
So, if group 1 is the most reactive metals, guess what group, Stavros, is the most reactive nonmetals?
Oh, 17.
Group 17, very good. So, I'm tying in everything I'm saying here. So this little diagram here explains this. As you move left to right, the metallic character decreases. What does that mean? It means group 1 is the most metallic, meaning the most reactive, as far as metals are concerned. And what does that mean? It loses an electron. Group 17 is the most reactive.
Wouldn't that be group 18?
No.
Let me finish my thought. Group 17, most reactive nonmetals. You guys are engaged. I like it. You're stealing all my thunder. Group 18 doesn't react. They're called inert. Why? They already have a full valence shell. They already have 8. Helium has 2. So the reason group 17 is what Stavros was saying. They all have how many valence electrons? 7. So all they have to do is gain 1 electron. So the opposite ends of the chart are the most reactive, not counting 18. Because that one's stable, they don't mix with the peasants, right? They do their own thing. So as far as the regular elements are concerned, the opposite spectrum here. 1 is the most because all it does is lose 1. Group 17 is the most reactive because all it does is gain 1. So if you put Na in the presence of Cl, guess what happens? Na really wants to lose an electron. Cl really wants to gain 1. So guess what happens when you put them together?
That happens.
What do they make, first of all?
Ions.
Salt. Right. It blows up. It's very explosive. I'll show you. I don't have chlorine gas, plus I wouldn't do it. It's too dangerous, but I'll show you online here. So if you take a group 1 and you react it with a group 17, it's a very vigorous reaction because Na is 281, Cl is 287. When they come together, they both achieve 288. Well, 28, sorry. Na is 28, Cl is 288. This 1 electron goes over here, everybody gets a full valence shell. Now, Na is 28 and Cl is 288. I know I'm going kind of fast and saying a lot. You don't need to know all this right now. All you need to know is the most reactive groups, and I'm explaining why. Something we've already talked about. This is really important. We'll go over this many times this year. So don't stress that right now. But that is all because of the valence electrons. Valence electrons are the reason all these things do what they do and they react the way they react. All right, good. Let's do a demo.
Do we need to take anything?
Nope.